Predictor variables, also known as independent variables, are the key components of a logistic regression model. They are the features used to predict the likelihood of a binary outcome. Here's a breakdown of their main characteristics. Number. Unlike linear regression, logistic regression requires at least two predictor variables to function. A single predictor wouldn't provide enough information about the relationship with the binary outcome. Types. Predictor variables in logistic regression can be continuous. They take on numerical values along a continuous scale, like age, income, or blood pressure. Categorical. They fall into distinct categories, like gender, male, female, education level, high school, college, graduate, or disease presence, yes, no. Categorical variables may need dummy coding before use. Interpretation. Coefficients associated with each predictor variable indicate the change in log odds of the outcome for a 1-unit increase in the continuous variable or a shift from one category to another in a categorical variable. Selection. Choosing the right predictor variables is crucial for building a good logistic regression model. Techniques like backward elimination or stepwise selection can help identify statistically significant and relevant predictors. Here are some examples of predictor variables commonly used in logistic regression. Risk factors for a disease: age, smoking history, blood pressure, genetic markers. Customer churn in a business: age, income, purchase frequency, satisfaction rating. Student loan default: income, debt-to-income ratio, type of degree. Remember, selecting and interpreting predictor variables in logistic regression requires consideration of your specific research question, data characteristics, and statistical assumptions. I hope this explanation clarifies the role of predictor variables in logistic regression. Understanding odds ratio step by step. Odds ratio, OR, is a powerful statistic used to quantify the strength and direction of a relationship between two categorical variables. It tells you how much more likely one event is to occur compared to another, based on a specific variable. Let's break it down step by step. Step 1. Set the stage with a 2x2 table. Imagine you're researching the link between coffee consumption and insomnia. You create a table with these categories: coffee drinker, not a coffee drinker, total. Insomnia: A, B, A plus B. No insomnia: C, D, C plus D. Total: A plus C, B plus D, N. Total sample size. Step 2. Calculate the odds. Odds of insomnia for coffee drinkers. Divide the number of coffee drinkers with insomnia by the number of coffee drinkers who don't have insomnia, C. A. Circa odds of insomnia for non-coffee drinkers. Divide the number of non-coffee drinkers with insomnia, B, by the number of non-coffee drinkers who don't have insomnia, D, B, D. Step 3. Get the odds ratio. Simply divide the odds of insomnia for coffee drinkers by the odds of insomnia for non-coffee drinkers, A, C, B, D. This gives you the odds ratio, OR. Step 4. Interpreting the OR. OR greater than 1. Coffee drinkers are more likely to have insomnia compared to non-coffee drinkers. The higher the OR, the stronger the association. OR less than 1. Coffee drinkers are less likely to have insomnia compared to non-coffee drinkers. OR equals 1. No relationship exists between coffee consumption and insomnia. Example. Let's say you find A equals 20, B equals 30, C equals 50, and D equals 100. Your OR would be 20 50ths, 30 100ths, equals 0.4 divided by 0.3 equals 4, 3 approximately equals 1.33. This means coffee drinkers are approximately 1.33 times more likely to have insomnia compared to non-coffee drinkers. Remember, OR is a relative measure, not an absolute risk. Consider statistical significance, p-values, to assess the reliability of the OR. OR doesn't imply causation, only association. This is just a basic example, and ORs can be used in various scenarios beyond coffee and insomnia. I hope this step-by-step explanation helps you understand this valuable statistical tool. Here's a lecture on logistic regression coefficients, incorporating an illustrative example. Understanding logistic regression coefficients. Introduction. Logistic regression is a powerful statistical method for modeling binary outcomes, e.g., yes, no, success, failure, presence, absence. It's distinct from linear regression in that it predicts probabilities rather than continuous values. Coefficients play a crucial role in interpreting the model's results and understanding the impact of predictor variables on the outcome. Key concepts. Logistic function, sigmoid curve, transforms linear predictor values into probabilities between 0 and 1. Allows for modeling nonlinear relationships between predictors and outcomes. Log odds. Logistic regression models the log odds of the outcome, not the probabilities directly. Log odds express the likelihood of an event occurring relative to it not occurring. Coefficients represent the change in log odds of the outcome associated with a one-unit change in the predictor variable. Positive coefficients indicate an increase in the log odds, while negative coefficients indicate a decrease. Interpretation. Odds ratios. Experiment, coefficient, provides the odds ratio, a more intuitive measure of effect size. An odds ratio of 1.5 means that a one-unit increase in the predictor variable is associated with 1.5 times higher odds of the outcome occurring. Significance. P-values assess the statistical significance of coefficients. A small p-value, typically less than 0.05, suggests a reliable association between the predictor and outcome. Example. Scenario. Predicting heart disease risk. Model. Log odds of heart disease equals intercept plus beta 1 age plus beta 2 smoking plus beta 3 asterisk blood pressure. Coefficients. Beta 1, age, equals 0.12. Beta 2, smoking, equals 0.46. Beta 3, blood pressure, equals 0.25. Interpretation. A one-year increase in age is associated with a 0.12 increase in the log odds of heart disease. Smokers have 1.58 times higher odds of heart disease, XP, 0.46, than non-smokers, holding other factors constant. A one-unit increase in blood pressure is associated with a 0.25 increase in the log odds of heart disease. Additional considerations. Interaction effects. Explore how the combined effect of two predictors differs from their individual effects. Standardization. Consider standardizing coefficients for easier comparison across variables. Multicollinearity. Address potential issues of correlation between predictors. Conclusion. Understanding logistic regression coefficients is essential for drawing meaningful conclusions from the model. By interpreting odds ratios, p-values, and considering model assumptions, you can gain valuable insights into the relationships between predictors and binary outcomes in various research and decision-making contexts.